to turn their camera on so I can see them. I would love to see the people who are on the call, but if you don't want it, that's fine too. You had suggested that I talk a little bit about some of the research. I'll keep it at a sort of more of an intuitive level, give some of the intuitions of the kinds of problems and projects that we're doing in my research group. And then I'll talk a little bit right at the end about sort of my career a little bit, just for a couple of minutes, I think. Now I had said half an hour. I think I'm going to run over, but I will try to stick to my time. I am definitely going to run over. I hope that's okay. Do you have a little time? So it's 45 minutes. Okay. All right. That sounds
Yes,
great.
45 per hour.
Wonderful.
Good.
Yeah.
Sounds, at some point, I'll have to run off
Oh,
meeting, but so
mhm.
that'll be the constraint. I'm going to share. Oh, I have to send request. Sharing is not turned on. So can you allow sharing? Okay. So let's me share these slides. Well, hang on. Did that happen? Don't think that did.
Also, I would like to tell the audience to write down your questions so that, like, since the topics we're working on at the research is correlated with the work of Professor Bala, you can ask questions later, so you can write them down.
Hi, and I see Fury. Hi, nice to see you. Okay. So can you see my slides okay? Great, wonderful. So what I thought I'd do is just talk a little bit about some of the research that we're doing sort of over the past 10 years in my group. Quick question before I go. Am I talking too fast or too slow? And well, probably not too slow. I never talk too slow. If I'm talking too fast, just type that into the chat and I'll slow down because I don't want to lose everybody. It's not a very useful talk if you're not keeping track of what I'm saying. All right, wonderful. So my group has been recently, so I work in computer graphics and computer vision as I was introduced, but more recently, actually for the past 15 years or so, my primary focus has been in computer vision and particularly more recently in planet scale visual discovery. So this is actually, visual discovery is an area that I would say we have sort of coined this term. A lot of computer vision is around visual recognition, visual understanding, and our research was aimed, and I'll talk a little bit about visual understanding today, but then our research was saying, what can we actually discover about the whole planet? Once, say I have great computer vision, it's working. What can I do with that to really understand the planet? And that's sort of the high level research goal of my group. All right. So you all know this, but I'll just remind you, visual data is everywhere. One of the things that has always shocking to me is the extent to which we are recording our daily lives. And I don't think people quite model that, how much we do. So whether it's regular cameras, I have two phones on me right now and a laptop, but regular cameras, all of us are taking pictures. But there's also camera traps. People are putting camera traps to record outdoors and wildlife. The street view cameras, of course, as every nowadays with all of the automated vehicles that are going around, there's a lot more recording going on of just driving scenes and daily city life. And then there's satellites. Yeah, yesterday I was walking outside and there's a string of satellites going out. There is immense amount of satellite data that's coming. When we started this work, there were about 50 odd satellites. There are 1,500 satellites in this past 15 years. So we are recording our life at an immense rate. And you all know, of course, that's just one piece of it. Satellites are one kind of data. We record videos, photos at a break at an immense capacity at Facebook, YouTube, WhatsApp, TikTok, you name it. And this just gives some smattering of the amount of information we're uploading daily. So we have all of this data. The question my group was asking is, what sense can we make out of it, right? One question, for example, is would it be great if we took all the satellite image data and actually understood, say, changes in city for urban development, for understanding urban impact on populations, or understand climate change? For example, lakes are drying, there's drought in some places, there's flooding in other places. How could we study that? Given that we have all this data, wouldn't it be great if we can use that information to study these kinds of phenomena? That was sort of what was motivating our work. And just to give you a sense of the scale of the data, we have 5 terapixels of information every week. Actually, it's more than that at this point. And finding, like, we can see that this lake on the right, for example, is drying, right? It starts off, there's some water, and so it's looping in a loop, and you can see that over time it dries out. But finding this kind
I
of
have a question.
event, sorry,
I have a question.
yes, go on.
What is terapixel? I know terabyte, gigabyte. What is terapixel?
Therapy, just so if there's each pixels, then it's correspondingly, so 4 bytes make 1 pixel. Let's call it that.
Uh, yes.
So images are made of 1K by 1K pixels, let's say. So 1 million pixels is in one image. And so this
Yeah,
is 5 terapixels.
I see.
Five.
Thanks.
Yeah. Yeah. Um, and good question. Lots of data. I think maybe the high order bit is there's just tons of data with the satellites that we're collecting. And finding these kinds of events is sort of finding a needle in a haystack. My student, this is a lot of the work that I'm going to talk about today was done by Utkarsh Mall. He's a PhD student, was a PhD student. My group graduated a year and a half ago, and now is a postdoctoral researcher at Columbia University with Carl Wondrich. And he found this drying lake. He can find the city kind of renovation that's going on, but it would be great if you have tools to automatically discover it. That's this field of visual discovery, which goes beyond just understanding an image to try to do higher level discovery of events. So, what are the kinds of things that we do? In our group, we looked at things like from Instagram images, recognizing cultural events and trends, and I'll talk about that. We looked at finding events like forest fires, drought, as I said, lakes drying, ecological events. And our most recent work is looking at how can you use these tools to give them to scientists so that they can do better scientific discovery. And so today I'm basically going to talk about those three projects. And I'll just give you a sense that these projects that I'm going to talk about are useful in a variety of applications, whether it's crops, monitoring crops, we work with crop scientists, whether it's understanding road network detection, understanding urban development, we work with urban development scientists, we work with climate scientists and people who are conservationists. So I'll talk about three different projects today. One is visual recognition. So first, let's start with understanding images, then understanding style. So this is fashion style, actually. That was the first project that actually got us into all of the satellite imagery. And then I'll spend a little time talking about the planet scale discovery in satellite images. Any questions till now? All right, so I'm going to dive in. One thing or should I pause? Okay, going to keep
No,
going.
it's going well.
Okay, good. One thing I'll say, you have to worry about privacy when you're dealing with images. And computer vision people deal with a lot of images. There's a huge question around ethics on how do you respect people's privacy. You're exposing things about their private life often. When sometimes satellite images are very high up, each pixel, right? An image consists of many pixels. Each pixel is 1 kilometer by 1 kilometer. Well, that's fine. You're not really violating people's privacy. But increasingly, satellite images have each pixel is like 60 centimeters by 60 centimeters. At that point, you're really getting into people's lives. You can see what they're doing in their backyard. You can see what they're doing in their houses. You have to be very respectful of privacy. So in our research, we actually will often blur the photos, the images of people that we're using if there are people involved. And we also, in fact, run our algorithms often on lower resolution blurred imagery and prove robustness even in that context. And in fact, one of my students, Lekha, who Gamechu knows, Lekha Revankar right now, just has a new paper on looking at low resolution recognition. I won't talk about that today, but it's important to remember that when you're dealing with any computer vision, think about the privacy and the rights of the people whose data you're collecting and working with. So with that, I'll start off with actually this video, which is unrelated, but it comes from a movie called Anon, and this in 2018. When this concept of the mind's eye, a person is walking around, and as he walks around, he sees ads, but he sees information about people. He sees the names of the people. He sees information about this car, exactly which car and make it is. And in this case, because it's sort of an AR, VR kind of a setting, he's also seeing a lot of virtual data. And I really like this. This is a very dystopian movie, by the way. So I don't know if you want to watch it. And it's a lot about looking at things like privacy, etc., and how we have to worry about thinking about those aspects. But what I liked about some, the vision of this world is that as you're walking around, you have this very rich interaction with this world. If you have a question about the world, sort of in situ, you can ask a question, oh, gee, I wonder what that car is. And it'll show you not only the make of the car, but all details so that you can think, oh, that's pretty cool. I'm into cars and this is of interest to me. So if you look at what the problems that this particular visualization was envisioning, and there's been a lot of work, as you know, recently, a lot of interest in Meta and Apple and all of these companies on doing mixed reality, virtual reality and augmented reality and mixed reality, which is what this is sort of envisioning. Now, this is going much further. It's saying that in your retina, you're going to have an implant that allows you to do this. Hopefully, we won't go there anytime soon. But with VR glasses and AR glasses, you can have these kinds of interfaces. So the problem, what I wanted to show is the problem that you're looking at here, when you see a car to recognize what it is the problem of visual recognition. The work of visual discovery builds on visual recognition. So the first thing I'll do is talk about visual recognition. And I do a lot of work also on graphics models for representing things. I know Gamechu works on that space too, but I won't talk about that today. So the visual avatars that you're seeing in the background, I've done a lot of work on fabric modeling and making images look realistic. I won't talk about that today. Sorry, you had a question? Did somebody have a question?
I think it was by mistake.
Okay.
If they're not speaking.
Okay. So the particular visual recognition problem is actually called fine grain visual recognition, because the coarse grain visual recognition says, oh, this is a car. But the fine grain says, okay, this is a hydrogen fuel cell replica, blah, blah. This is a fake car, but that's what it would say. And this problem requires expert knowledge, right? No random person off the street would recognize the details of such a car. You need to be a car connoisseur to care about this. And in fact, when my student and I started working on it, so this goes back a decade. We started working on this in 2014, so exactly about 10 years ago. My student, Sean Bell, he was getting his PhD in my group, started looking at this problem. And we actually came to it, we were looking at material recognition, and we were looking at photographs online in a company called House. And House, we found a lot of people would ask questions. This was about interior design. People would post questions or pictures of their kitchen, very nice kitchens. And then they would say, oh, I wonder what is the countertop. I wonder what is the chandelier. People who are looking at influencer photos will say, here's a celebrity. I wonder what that handbag is, right? So these are the kinds of questions people were asking. And what we realized is other people would type an answer then. This was 10 years ago. But we needed to automate this problem. That was our research problem. We decided this clearly needs to be solved with AI. That's what we're going to do. And so I'll give you an idea of how we went about doing this. So I'll give you this example. Here is something that is somebody's backyard. You may or may not recognize what kind of object it is, but imagine you walk into somebody's backyard to say, this looks cool. I wonder what it is. You take out your phone and you take a picture and you say, what is this? That's the problem we were solving in this research I was doing with my student, Sean. And it turns out it's a sculpture. It's a fire bowl, actually. So you can use it people use it as a fire pit in their backyard. And it's produced by a particular artist in California. So that question of fine grain recognition, not only recognizing it's a fire bowl, but specifically this fire bowl, was a problem we wanted to solve. So the challenge is you have these beautiful pictures from the company that produces it or from the artist that produces it on the left. These are product images that they put on their website. And then in the real world, when people actually install these objects, if you look at the bottom row on the right, you can see 3 different pictures of the fire bowl in the real world. And it looks very different in the real world compared to how it looks in a product website. And so our problem was trying to figure out how do you correlate these iconic images, clean images, with these messy real world, in the wild, so to speak, images. That's the phrase that's used, in the wild. And to do that, and I don't know how many of you have done enough machine learning to understand this, but 10 years ago, deep learning was just taking off. We were just starting to work on improving computer vision algorithms for recognition. We essentially looked at the problem there and realized that the learning that we could do, we can create an AI algorithm that uses the deep learning. We'll use a Siamese network, actually, and we can learn how to match these different kind of images. What I'm going to do today is give you an intuition of what this does, because it turns out the particular approach they use, it's 10 years old, but it's still used in modern times, in modern deep learning algorithms. And so the particular algorithm is what you're trying to do in this case is find an embedding. And if you don't know what an embedding is, think of it as a map. So you can think of every photo in the world has a particular place on the map that's its home. Okay. And so when you have a photo here, for example, on the top left, it projects to a particular point in the map, which is the embedding. And what you want to do is have all the different photos, even though it's taken with different lighting, different viewpoints, different cameras, all of them to project the same point on the map if it is the same object, right? In this case, this particular chandelier. Meanwhile, these other objects are not the same object and they should go to a different point of the map because they live in a different part of the world, if you will, right? So that's one way to think of the embedding. It's this map where similar things are close by and dissimilar things or different things are far away from each other. And that's really intellectually all that the deep learning algorithm learns. It learns this map. It learns how to project something. So then now when you ask the question, what is this? It looks it up, projects it into the map, and it finds, oh, it's this particular product, the Hamel ring in this case. Okay. So how should you learn this map? As I said, I'll give you a little sense of how to do this. There's much, much more detail that I won't cover, but I won't introduce the concept of contrastive loss because 10 years later, contrastive loss is still used very heavily in a lot of machine learning and AI algorithms. So the idea in contrastive loss is you map through a deep network, right, a deep neural network, and you're learning the parameters so that you map that image into some point in this map, this embedding. And when I say it's a point, it's a high dimensional point. In this case, I think it was a 512 dimension point that you're mapping. So very high dimensional point, in fact. And what you want to do is you want to take all the images of that same object and try to map it to the same point. Now, when you start off, they map to different parts of the map. And what you do is you set up a loss function to pull them close by. So you say these 2 points should be at the same place, but they are far away. Let me set up a loss function that pulls them close by. So you set up a loss function that pulls them together. And meanwhile, when you have a negative example, a different object, you set up a you set up a loss function that pushes them away. And I won't get into the gory details, but that's actually a relatively simple idea. Similar things should be pulled together. Different things should be pushed apart by a certain margin, a margin M. And you can actually just write out the equation. And then your problem as an AI, your training algorithm, what it does is it trains, in that case, this was 10 years ago, took us 2 weeks to train this algorithm. Over 2 weeks of training, it learned that map. It started off with everything all jumbled around and slowly sort of settled out so that similar things were in the same place. They were pulled together, different things were pushed apart, and the new map had a lot of consistency to it. That's the high level idea of contrastive loss. And to this day, contrastive loss is used very heavily in robotic learning, in computer vision, and many, many other AI algorithms. And that's why I thought it'll be useful to show it. So here's for sort of an example of the map that we learned. And you can see all these spots are similar looking. They're different from these spots. And this was done for home decor objects, so you can see. And I'm just going to run the video and you can see that that's the big map. It's complex. But when you zoom in on any part of it, you'll see a lot of similarity to the objects in that part of the map. And a lot of, different parts of the map have very different things. That makes sense. So that's the 2D map you're learning. Once you have this, then here, let me go. Now, when you ask a question, what is this object here, in this case out here? And sorry, that's a little displaced, but this is a particularly challenging example, this chair, because it's basically a transparent chair. It's made of plastic and you can see right through it. So it's very confounding from the number of pixels that actually show the chair. Your brain is doing a lot of analysis to understand that that's a chair of a particular kind, and you're not seeing the background, you're not getting confused. And we were able to essentially in our top 3 results figure out these chairs were very popular. They were called the ghost chairs because they're basically transparent. And on the third hit, you can see here, 3 of them are very similar, and the third hit is the exact match, including having the right arms, etc. And so the top 3 to 5 hits typically were actually very accurate. So Sean, as I said, did this with us, and this was such an effective approach that we decided to form a company called GrokStyle. as was mentioned in the introduction, to do this kind of search. And here's another example. Oh, this is a fun one. If you walk into somebody's house and see this chandelier in their dining room, it's almost impossible to describe what it is, right? You can say, I want a chandelier, it looks kind of bubbly or cloudy, but you can just take a photo of it and it'll automatically find out it's called a tiara chandelier. In fact, the first hit exactly finds the match. And it's a hard one to describe. So that's one of the benefits of this visual search. It lets you find things that are actually hard to put into words. All right. So as I said, Sean and I decided we'll start a company, Grok Style, on it, and based on this technology. And we, in fact, partnered with IKEA at that time. Do you have IKEA in Ethiopia? Have you heard of IKEA? No? Okay, but you've heard of IKEA? Okay, IKEA is a big furniture company from
We've heard of IKEA.
Before we move on, can I ask one thing?
Yes. Yes.
So you mentioned with the contrastive loss, you're trying to pull similar things together.
Yeah.
But then what's your metric for deciding what things are similar? Are you looking at the use case of the object or the shape or?
Very good. So in that case, and this is 10 years ago, and we'll use contrastive loss in almost every project I do, and in each case we use it a little differently. But in that particular case, we had data. We had the product data from the actual products, from the catalog. So in fact, we talked to IKEA, and we had IKEA's products, right? So we'd have their photos, we'd have their photo. It was very clean. It was done in a laboratory setting. It was done in their photo studios. And then we also had user pictures. People love IKEA products. There are entire Instagram accounts on my IKEA, this and that, and people show how they use their products, how they have it in their house. So we had user photos and we had the products from the company. And that was what we said are similar, right? Because we knew they were the same, they were tagged the same. So there's data, which is labeled data that comes from the user and from the company that we tag. In the last project I'll talk about, we do unsupervised learning. There's no data. So we actually do clustering and do unsupervised recognition. But that's a great question. And I'll show this again, sort of this video. So we launched with IKEA. You can see
Maybe I
where.
can ask a follow-up question.
Sure. Let me just walk through this video. I'll just say this and then I'll answer the question. So we recognize the IKEA products and then we can actually do this relates to my other research. We can swap in other graphics models and actually visualize your indoors. We can actually find different products that match your particular armchair and we can help you design your home. That was sort of the high level idea. Yeah. What's the next question?
Yeah, so on the contrastive loss part, so the same objects are put together on the map on the same area, and different objects are found on the are pushed away. So does the direction on which the objects are pushed away matters? Like, what's the direction?
It's set up in that high dimensional space. So you push it out you do basically a component wise distance and just a square distance and you push it away that way. So it's pushed out effectively. Sorry, let me go back. The main thing is that you have this sort of a hypersphere, a high dimensional sphere around which you push things outward, away, just outside that sphere. And different ones, depending on how different they are, will be pushed in different directions. Over time, if you iterate enough, it'll still find its place to the right location. Okay.
Okay.
I have one question.
And let me go back. So then we did this with IKEA, as I said, and 2 years in, Facebook reached out to us. They wanted that visual search capability. So they actually acquired our company, and Grok Style then went into Facebook and became Facebook's new searchable, make every image shoppable was their tagline. They introduced an architecture called GrokNet, which was built on Grok Style. That actually Sean is still in Facebook now. It's Meta. Actually, essentially built the AI visual search tool within Facebook's engine that used our technology. And it's used not only to recognize, for example, you can see this rose pink tea kettle in the left, but on the right is actually used to recognize attributes. For example, here's a wool and cotton rug or a vintage Turkish rug. And in fact, those attributes are very useful when you're selling things on Facebook Marketplace. Those attributes are what you use to match things. Okay. All right. So that's the visual recognition. And now we'll talk about actually how we use it for visual discovery. So one project that we started doing is looking at fashion. And I'll just give you again a very high level idea here. But the high level idea was we knew that we could do this recognition. So we wanted to understand how people dress around the world. Okay. And we call this street style and geostyle. And it started with Kevin Madsen when he was here, but then Utkarsh, when he joined my group, started to work on it. And it started in 2016, but then the project really continued for the next 4 years, and we published in ICCV in 2019. And there again, we're using supervised learning. We have some number of attributes for images. For example, here's an image. We say there's a round neckline, there's a hat. We have 12 attributes, sorry, that are annotated in each image. We have a small amount of data, 27,000 images that are annotated. And then for 8 million images across 44 cities, we learned this embedding again. So that's why I wanted to introduce the concept of the embedding. Essentially, once you have that technique, now you can learn an embedding and you look at it, maybe things don't jump out, but let me just quickly show you. There are clusters where there's actually very similar styles in this case. Earlier, it was similar products. Now you can see on the top right, for example, there's lots of green clothing. And so we found these style clusters. And you can find things like people wearing jackets or people wearing stripes and people wearing plaids. So now we've discovered how people are dressing around the world. So that was step one. That was very fun when we first did this. And step two is actually you can then plot these clusters. So here are four these were highly relevant clusters. And there are four clusters, and each of them shows something quite distinctive. So on the left, you see the cluster. On the right, we show from which city you're getting data for that cluster. On the x-axis are the 44 cities. On the y-axis are the months of the year that we got from the images that the photo was taken in. And you can see in the top row, I'll just walk through the top first row, is this gele, is this particular headgear that's worn in Lagos. And there's some noise in the data, but we have found something that is very culturally relevant to one part of the world by just analyzing the data. In this case, we had never heard of the gele. Sorry, we live here and we didn't know about this particular headgear, but we've discovered something interesting to the people who live there. We also found a lot of people wearing hijab, across the world, but particularly in Cairo and Jakarta, a lot of the Instagram images had people wearing the hijab. And those are sort of geographical, but you can also find temporal changes. For example, people were wearing hats and jackets, black jackets and hats, and you can see on the right that you can see that it happens in winter. And in fact, on the right, you can see in the northern hemisphere, the winter happens in December, which is the bottommost row, and January, which is the top row. But there's also some countries from the southern hemisphere, and there you can see that jackets are worn in the middle of the graph. So we actually can start to see trends across the world, things that we didn't necessarily know about. I mean, we knew about winter, but some of these distinctive trends were new to us. Could also find unique events. So for example, this is data from 2014. This was a big spike we found for a t-shirt, yellow V-neck with graphics. Anybody have any idea? This is 10 years ago. You probably don't know. But there was a big spike, and we actually went and looked at the part of the world it came from, and it turns out it was the World Cup. So the World Cup, which happened in South America then, there was a huge spike of people wearing their team sports or posting images of their favorite team, the team that they were rooting for. And it happened to be big in Brazil, and you were seeing that just pop right out of the data. And in fact, we can do this for the whole world and capture different cultural events. So on the top left, you see in Seattle, we found St. Patrick's Day in March, where people wear green. We found World Cup, I told you, in Rio de Janeiro in the Southern Hemisphere. We found in India, I know India pretty well, there's this thing called Durga Puja in Calcutta. If you don't live in India, you probably don't care about it. But if you live in India, it's huge. Like everything stops, the whole city stops, and this just pops right out in the data. You can see people are posting a lot of images of them at that time. And so this is a way for us to understand worldwide cultural events, even if we didn't live there. And we actually worked with an anthropologist whose job it was to understand these images. They loved this tool because normally the way they learn this stuff, they have to go and visit a place, live there for 6 months, try to talk to people, try to understand what's going on the ground. Whereas here, it gives them some data, and then they can go and still do all of those things, but it gives them a lot of powerful sort of pre-information so that they can go and be effective when they land up in the country. Okay, so that was this trends and cultural events. I'll now just briefly talk about sort of more recent work that's been going on for the past couple of years in my group. And one of you asked a question, where are you getting the labels? In all the previous work, we were getting labels from the data from the products or from a user annotating some of the clothing. But what we wanted to do is find worldwide events around things like, so I just want to quickly explain this. On the top and the bottom row, on each column is a particular event. On the leftmost, you can see crop changes. So there was a crop and then it was, harvested. The next row is a forest fire. That blackening is an entire forest has been basically destroyed with a fire. Road construction, you can see in the third column. The fourth is actually Yellowstone flooding. There was a huge flood in Yellowstone National Park in 2022, and you can see that immediately in the satellite images. And on the right, it's a little more subtle, but you're seeing actually the drying of a big lake. And so the water lines, there's more and more beach coming in, but there's basically a drying lake that's happening. So given all these visual events that are visible from space, we realized that like our geostyle and our street style work, where we were recognizing style, you can use some of those concepts and apply it to satellite imagery to discover climate type events. But you need labels, right? So the question was, where do you get the labels? You can ask a scientist to give me labels and say, here are road constructions. An environmental scientist could say, here are forest fires. And then, and keep going. And by the way, these videos are looping. So that's why they go to black and then they loop back. So you're seeing the change over time in each one of those videos. So that's one way of doing it, but the annotation is costly. Each scientist has to spend time for their application and they have to know what they're looking for. But our whole goal is to do discovery. Maybe we find things that we don't know that already exist. So to do that kind of discovery, we need to actually flip this around. And so Utkarsh's work basically flips this whole pipeline around where it does unsupervised learning. So it takes these satellite images, it then does detection and clustering of these events. And it's essentially trying to find similar events and cluster them in this high dimensional space. And I won't get into the details of the model, but it's in this NeurIPS paper from 2022 and a CVPR paper from 23. And once we do that, we have these automatically discovered events. There is contrastive loss that is used, by the way, in this again, to find things that are similar. So we find, for example, road network growth, but not only in an image, but across time, and we cluster them together. And you discover these events automatically. And then the scientist comes and says, oh, this looks like a road construction. This particular cluster looks like it's urban development. This other cluster looks like a forest fire or a water level. So you can have the scientists name the events, and sometimes you might find new events that the scientist didn't realize was there, but actually pops right up. So it's much more cost effective, and it discovers new previously, sort of open vocabularies, discovering new things that we hadn't realized we were looking for. I'm going to the last leg of this thing, and I'm going to give, again, I'm sorry, I'm doing this all very quickly. There's a lot of detail in each one of these projects, but Gemeche can point you also, and of course, you can look at these papers if you want, and we're happy to engage with anybody if you send us questions. I'm going to talk about the last project that then built off. So I told you everything that I did up till now. This one, for example, was in CVPR 23. And as you knew, large language models or foundation models kind of showed up. ChatGPT showed up around end of 22 or beginning of 23. So when ChatGPT showed up, there was a lot of excitement around language models. And then what were called vision language models, so VLMs. And CLIP is a very good model that came out, which connects up internet images with language models so that you take any internet image and ChatGPT can give you a caption for it, for example, and describe what you're seeing in that image. I'm assuming all of you are aware of this and you played a little bit with language models of this kind, right? So our question was, that's great. Can we do that for satellite images? Internet images have all of this. So remote sensing or satellite images, is there a similar thing? I show you a satellite image and you tell me what I'm seeing in it. Turns out there isn't. And there isn't because satellite image, there's huge amount of data. Remember, I started with saying there's tons and tons of data. but there's no labels for them. Nobody labels all of these images. So there's no connection to the ground, on the ground events that are happening. So there's no connection within a vision language model of satellite images and language models for like ChatGPT. So that was the work that we did in ICLR 24, where Utkarsh essentially produced, and Cheng, who was also a student here, also graduated last year, produced a vision language model for remote sensing. So I'll give you the intuition. The goal is where are you want to be able, a scientist should be able to ask these kinds of questions. Where are the farmlands in New York State? And just give you a whole bunch of satellite images. And it should produce a map like this and say, by the way, here are where the farmlands are. So you can see in the big cities, which is New York City is further down here, not so much farmland, but kind of where we live, which is the Finger Lake regions in Ithaca, New York, there is a lot more farmland, which is true. We live in farming country here. So how do you go about doing this? It's our friend, the contrast of loss, which is why I wanted to introduce contrast of loss earlier. So what you need to do is connect up satellite images with text, which we don't have. But we have something which is lots of ground images with a connection there. So we use that as sort of an intermediary, and we create sort of this triangle, a stool, if you will, a triangle, if you will, of a connection between satellite images, regular images, and text, so that we can learn the connection between satellite and text. So we are learning the blue arrow, and we're learning the blue arrow by connecting up clip-like models that connect up a ground image with text. So on the bottom arrow, you're seeing a ground image and a text that says a river with a lot of trees on the banks. That is what a current VLM will produce. And then that diagonal orange arrow is using geotags. So each image knows exactly where on the world it is. So you can connect up with which location it is in the satellite image. So you have many, many images on the ground that connect up to one location in the satellite image, but you have that intermediary connector that then lets you connect the satellite image to the ground description. Does that make sense? Okay. That's the high level idea. And to do that, as I said, you use contrast of loss. So you connect these two images up, aligning them using contrast of loss, the same as I started off earlier. And then you also have your text, and you're learning essentially, we call this graph because it's ground remote alignment for training VLMs. And once you do this, you get a lot of power. So now we can do earth monitoring with text description. So for example, we can say, tell me where all the crops are in New York State. And on the top is what we produced. On the bottom is a ground truth map that came from a survey. And you can see we're incredibly accurate. I mean, and we have more metrics to measure it than just a visual inspection. But I wanted to give you a sense of an intuition of how well this is working. On the top here is a road network detection. Show me all the roads in New York State. The bottom is again the survey data. Again, you can see that we found all the major arteries, the major highways, and some minor roads, which is exactly what you would hope it would do. And finally, this is for forest conservation. Where are the forests in New York State? Again, we're able to show where they are actually accurately on the map. So that's one use case. Another use case, which we got very excited about, is actually connecting it up with programs. So Carl Bondrick in Columbia, who was one of our collaborators, actually produced Viper GPT. If you haven't seen that paper, it's very fun, which actually converts any question that you ask about an image. Say, is this image got a human being eating food? It'll write a program that will recognize people, recognize food, show the act of eating, and write it as a program. And the benefit of this is you have an interpretable understanding of what's going on in an image. So for example, if you ask the question, here's an image, can I bike and can I swim here? It'll do a patch-based analysis. It'll find bike paths, and it automatically produces this code, by the way. It'll find bike paths. It'll also find swim areas, and it'll say, yes, is there a bike path and a swim area that are close by to each other? If so, the answer is yes. So we connected up then our graphed algorithm with Viper GPT so that a scientist can then ask these kinds of questions, very high level questions about a satellite image, and we are able to produce results that actually are useful for a scientist. this particular approach of asking programmatic questions, like converting questions into programs that have a combination of deep learning black boxes inside the program and interpretable programs outside, is our current area of research. And we think it's very, very promising, because scientists don't want black boxes. They want to understand what you're doing. Otherwise, they can't prove that you're doing something hypothetically, your hypothesis is sound. And so we're working a lot more on interpretability of deep learning. Okay, so that's it. I told you I'll take 45 minutes, and I did on the dot. That's what I wanted to say. We are working, those are the three sort of sets of projects. I'll say what I love most about it is we're working with experts, cultural anthropologists, fashion designers, crop scientists, biologists, climate scientists, and now policymakers, as we are trying to do discovery in planet scale, at a planet scale with satellite images. One project I didn't talk about is we're looking at understanding the destruction of archaeological sites in Armenia. There's a big conflict between Azerbaijan and Armenia, and we're actually tracking which cultural heritage sites are being preserved or being damaged. We're working with people in the global south who are looking at tracking disease in water. So there is this particular disease, which is actually, I won't name it exactly, but it translates into snails in the water carrying that disease, and it then transfers to human beings and kills people. So what we've been tracking is actually the prevalence using satellite images to understand where the snails are, where there's the right underwater vegetation, and then use that to track disease spread. All of this work that I talk about has been done by amazing collaborators and students. I want to just give them a nod. I really am honored to work with really amazing people. And I'll pause here. I'll say a little bit about myself. Maybe I'll just 1 minute and say, I started, as I was mentioned, I did my undergraduate at IIT Bombay. Actually, I think I have a slide. Yeah, oh yeah, I have a slide, my journey slide, yes. So I was born and raised in Bombay, in India. I was the only woman in my undergraduate class. You can see a picture of that in the top right, and in computer science. So I went to undergraduate in the Indian Institute of Technology in Bombay. Then I came to America to do my PhD at MIT. I came to Cornell to do my postdoctoral research, and I've been at Cornell since then. So I've been an assistant associate and full professor here. I went off to do Rockstyle for a couple of years, but then I came back, became the chair of the department, dean of the college, and now I'm the provost. And I just want to say the journey, I have an incredible family that supports me, and incredible peers and colleagues. I will say all of this work, I'll go back to this slide, has been done by great students and colleagues that I've had the pleasure of working with. So happy to take questions about this or anything else.
That was a
I have a
very
question.
Has been
fascinating.
really nice.
Yeah. If anyone has any questions, you can raise your hands and ask them away. I know we have
Can
one
you-
question prior as well.
Can you hear me?
Yes.
Okay. Hello. It's nice to meet you. It's a very inspiring talk that we had. I'm currently transiting, so I hope you can hear me. But
Yes, can hear you.
Okay. My question was, you mentioned earlier that the space that we used was very high dimensional, 512 dimensions you mentioned. My question was, what is the significance of such a high dimensional model? Because can it not be represented in a lesser
In a lower
dimensional
floor.
space as long as it's used to hold the items in a lesser dimensional space?
I think that's a great question. And I'll say when we started, and this was the first project, again, each project used a different dimensionality. But the first one, we started, actually, it was 256 when we wrote our original paper, 512 when we went internally when we were building it. And you're exactly right. We started off initially with these higher dimensional spaces as we were learning and understanding. But you can definitely distill it down to a lower dimensional representation. And that's something that we did do because it's more efficient, etc. But in our early days, we were focused very much on accuracy. So we picked the highest dimension we can afford to train to at that early point. And over time, we appreciated that you can get away with lower dimensions and operated in that. So in fact, the work that I would say, again, it's not so much focused on dimensionality reduction. It's more around image scaling. But Lekha, who's on the slide here, and it's her most recent work, which is going to get published this year, actually is looking at this knowledge distillation where you can use much more compact models that represent the much more complex concept earlier.
Okay, thank you very much.
You're welcome. Firi, did you have your hand up? I thought you did.
Oh yeah, I had. For like the satellite data, um, like that tracks like the snails and like the disease. Do you also use like you know studies or like locational data? Like for example, let's say in somewhere in Ethiopia or Congo, like this river is known to have let's say hold this type of virus and stuff. Like do you use that to like buffer the insight you're getting from the model?
That's a great, yes, absolutely. So firstly, I'll just say we use even multi-scale data. So in local places, sometimes a municipality will have, or some nonprofit, an NGO will have drone data. So they will have that kind of data that they've collected on the ground. We correlate that with the satellite, and we correlate that with ground measurements of higher incidence versus lower incidence. And that's exactly the point of this. So the point of this particular research is get every kind of data that you can get, try to learn good models, because the problem is hard. You're looking at underwater vegetation from a satellite image. So you only see it when there's a very heavy bloom of that vegetation so that it's actually visible all the way from the satellite image, even though it's underwater, right, for the snails. And so we use all of the correlated data. And longer term, and we just have started this project with this group, our hope is to then use it to infer in places where there isn't drone data, et cetera, right? So generalization of our models to other areas, and to continue to correlate with municipalities and stuff. I think there is a lot of information that we want to connect up with the visual data to then make inferences on health and health outcomes and policy outcomes. You can even find some places that have more pesticide, some places have less pesticide. We want to collect all of these data points to understand impact in spaces.
Maybe one higher question.
Yeah.
So it looks like for satellite data, we just need a computer vision algorithm to detect all of these things. And all the knowledge we have from graphics, like the material and all of them, we don't really use of those knowledge in these techniques. Like, is there a way to use techniques? Like we can use the graphics knowledge here?
So I came to this from material recognition, right? That's why I was doing this research. So I was doing research on material models in graphics. Then I started doing, Sean and I were doing material recognition. We produced these intrinsic images in the wild, materials in the wild. We had multiple papers in the space, open surfaces. We had multiple papers producing data sets to do material recognition. And that's how we got into our visual search. The material is sort of implicit in it. It is, in fact, part of it. So when we look at the health of a tree or a plant, a healthy plant or a healthy leaf versus an unhealthy leaf is baked in. So there's that material that's baked into the visual features. But you're right, we're not doing it in separating it out as geometry versus material. And we're saying, oh, the tree is looking like it has mildew in it, for example, and we detected that. We're not explicitly doing that. We're baking it into the geometry and the material. It's a good question. I think there is a time and a place for using that knowledge. It's not clear in this particular project. That would be the most useful. But we started working, and this might be of interest to you, Gamechu. We started talking to people who are looking at diseases in grapes. So they are they are with wine growers, and they are in Geneva, New York. So they're actually 1.5 hours away from Ithaca, but they're part of the Cornell extension. And we just started talking to them, and they are interested in potentially characterizing sickness in plants, for example, and their material recognition matters a lot, right? Because you actually want to recognize healthy versus less healthy versus very, very unhealthy. So we're starting to work on that space. But it's useful if the application requires it. So if the application requires you actually inferring how diseased the plant is, then the material properties are useful. If all you want to know are yes, no, diseased or not, then you don't essentially need to go all the way to the material.
I see.
Does that make
Thank you.
sense?
Yes, correct.
So yeah, we do it driven by the need of the application, I would say. Okay.
I had one
Any-
question related to the discovering events using satellite images. You said
Yeah.
that you use contrastive loss to compare between the images, but then not only just the images themselves, but also through time.
Yeah.
So how does that work?
It's so there's multiple different parts of it. Let me see if I can. There's one. Okay, so one, for example, I'll say there was a project. There are 4 or 5 different projects in that. So I kind of buried a lot of projects into this one sentence that we use contrastive loss here. In one of the projects, for example, Utkarsh identified that the problem we have is look at a satellite image. There's a change that's happening because the snow is falling and the snow is melting. This is seasonal change versus people are changing the city year on year, right? So what he decided is we need to change the loss function. It was a contrastive loss function so that short-term changes that are very big. Actually, when snow comes versus not, the image looks very different. Big changes, but if they're short term, you ignore them. Whereas if they're long term, even if they're smaller changes, because you added a road, you keep those. That's kind of subtle, right? So you're this is the thing with these images, they're confounding you by big changes coming because the weather changes, the sun actually sets and the satellite takes it at different times of the day, shadows are different, and the image is very, very different day to day. But actually, over the years, it's very subtly different, but it's that subtle change you want to capture and not the dramatic change of the snow falling on the ground. So that's where he actually messed with the contrastive loss function and actually specified correctly what's the timeline over which you pull them together and what is the short-term timeline, even though it's dramatically different. You don't bother pulling it together, you just leave it alone. Actually, no, you pull it together when it's a short-term and dramatic change, but push it apart when it's a long-term change, because long-term means it's a real change. And that's how we are finding these long-term changes over time. That's one of the projects. There are two other projects on the clustering, and they use it a little differently, but that's one example.
A
And
more
I'm happy.
general question, maybe, to find
Yeah.
everyone. So you mentioned interpretability, and considering I'm an interpretability diehard,
Okay.
the thing with computer science researchers that I noticed is there's a lot of friction when it comes to interpretability. Lots of the researchers that I talk to would say something like, if it doesn't improve performance, then, why would we care? So, especially like when we were talking about mechanistic interpretability on black box deep learning models. So, what do you think? What does it take to actually make interpretability something that, I mean, I feel like it's the most important topic to work on. What does it take, to actually make it a mainstream research to work on?
I mean, I think it is. I think it is a mainstream research project because I'm working on it too. No, I hear what you're saying. I actually think what's happened is interpretability was very hot 8 years ago. Then we didn't make progress. Performance dominated, right? A lot of performance dominated, and then so it kind of the interpretability was not being very useful, and additionally it was not being performant, so it's neither useful nor performant, so people stopped working on those avenues of research, which I understand because it's useless and not very good, right? I think that's actually turning completely changing now. So I particularly like, and I really recommend read the Viper GPT paper. I like this idea of going to programmatic approaches. Programmatic approaches have interpretability. Not only do they have that, we have proof systems. We have, code, understanding code. We have a huge amount of computer science mechanisms that understand programs that proof-based learning, proof-based language, programming languages, etc. So that line of work, I think, is back in play, and it'll still have a black box in it. But now the black box has, there's a combination of black box and interpretability. And I think that way you keep the performance, but you actually keep the interpretability at the right level. So what we have figured out is this, what we believe, and this is Bharat Hariharan, who's actually Gemetru's advisor. Bharat and I and Carl are working on what we're calling programmatic foundation models or programmatic large language models, right? And the idea is the performant part of a black box computer vision, we're still keeping inside because those are really good. We're recognizing whether a road is a road, that using the deep learning algorithm for that is the right thing. But understanding an entire network of roads and understanding that they lead a particular way or don't lead a particular way, that's a higher level sort of cognition question. And that is better done through a programming interface. So our argument, our position is that you want that combination of black box and symbolic reasoning, and together you will arrive at the most performant and most interpretable outcome. That's sort of where we're betting. There's a lot of work to do in that space, but I think that's actually, it's gaining a lot of traction. So I think it's going to be increasingly an important space of research.
I had one more question that I asked earlier, but just to repeat it. So I noticed that you worked on light cuts.
Yes, a long time ago. Yes.
Okay. So light cuts, basically the idea is that you create, well, basically you break down the rendering of different light sources to make it more efficient, right?
Yeah.
Okay, so my question was, how much was it implemented on devices? Because I feel like its efficiency would skyrocket, as lights are the major problem in rendering. It takes a lot of time when there's one more light added to a scene in 3D applications. So has it been implemented on any 3D application, you know? And do you know by how much that it betters the efficiency of the rendering?
Right. So just to, this is not work I talked about today, but light cuts, the idea is it's in 3D graphics. You have thousands of lights. When you have a model of a big building, you have thousands of lights. Every light fixture is a light. And how would you render a scene? Traditional algorithms will go one by one through each light, order n. That is crazy. So it's light cuts was essentially a clustering based algorithm. You cluster all the lights and you find the most important lights for each part of the scene that you need and approximate all the other lights with some approximation, and we bound the error of the approximation. That's the high level idea. It was actually used in Autodesk's 3D render, and it's actually still, as far as I know, in Autodesk 3D rendering. So Autodesk's, all of their 3D rendering actually uses a light cast based mechanism for light simplification, if you will, or clustering. So very much used in production. And it has formed the basis of many people actually how they think about large scale lighting in complex things.
That is incredible. I really like rendering and 3D applications, so that's great work. Thank you.
That's great. Yeah. So Autodesk 360 rendering, I think it was called. That was the online render that they used, was based on light cuts. And Bruce Walter, who is actually one of the chief architects, actually that's his picture there, is at Cornell, and he's a person who was sort of the chief architect of light cuts, and he has really done amazing work in that space.
Okay, thanks.
You're welcome. Enjoy rendering. It's fun.
Will do.
All right. I know it's on the clock hour, and I said I'd wrap up at 45, so I should probably head off. But these are amazing questions. It's an absolute pleasure talking to this group and having you also engaged. Enjoy the rest of your evening. I guess it's Friday evening at 4 o'clock there.
Yes.
Yes.
All right.
And before you leave, we would love to thank you for your amazing presentation. So far, we've been learning a lot about computer vision, and today you opened our eyes into visual discovery, which is a new aspect of computer vision. And we really thank you for giving us your time and explaining all of this.
Happy to do it. Thank you. Thank you for inviting me. I really appreciate it. And enjoy. And I'll talk to you, give at you when you come back to town.
Yeah, thank you.
Take care, all. Thanks. Best of luck with everything.
Goodbye.
Bye.
Thank you.